So I'm going to talk about a few numerical experiments that I've been working on the interplay between star formation and stellar feedback in galaxy formation simulations. And this is work I've done together with Andrei Kravtsov and Nick Liddon at the University of Chicago, and also Sam Leitner. So I don't think we have to reintroduce the issues that exist in galaxy formation theory, but so I'm just going to jump straight into how I view the sort of star formation feedback cycle. So this is an Ouroboros, so the serpent eating its own tail. And the problems that we usually have is that we are thinking about star formation and feedback as separate entities, but in reality, of course, everything is connected, as you're probably well aware of. So star formation will generate a certain properties of feedback, and feedback will generate in turn outflows and turbulence in the interstellar medium and in the intergalactic medium, which in turn influences star formation and so on. And the big question is for modelers is, so which models of star formation and feedback achieve reasonable galactic characteristics, and are galaxy formation models degenerate? And if so, how can we break those degeneracies? Do we need just more data, or what can we do? So I'm just going to start from the feedback scale, and this, what I'm showing you here is the luminosity output from a single stellar population taken from starburst 99, and so it's the luminosity as a function of time, and I'm plotting you here the bolometric luminosity of the starlight, the wind power or the wind mechanical luminosity, so of the stellar winds from young massive stars, and the mechanical luminosity from supernovae. Okay, as you can see, supernovae explode only after roughly 4 mega years after the birth of a single stellar population, and before this time, stellar winds and the radiation field from the young stars have already preconditioned the star-forming regions. And what's interesting from this plot is that the momentum injection rate from supernovae and winds have roughly the same magnitude, the L mechanical over the typical velocity, a few thousand kilometers per second for these processes. And that happens to be roughly equal to the radiation momentum injection as well. So the volumetric luminosity of starlight over the speed of light. So all of these, the momentum injection rates from all of these different mechanisms are roughly the same, and this is probably why we should consider all of them in our simulations, or try to understand anyway if any of these are more important than the other ones. So this is what we have done. So this is here's a matrix of the terms that we have in our feedback recipe. So the energy injection is coming from supernovae and the stellar winds. Momentum is coming from supernovae, stellar winds, and the radiation. And we have mass loss and metal enrichment from various sources. Okay. So, and these are all again calibrated on stellar evolution codes like starburst 99. And this is something that's been more popularized, I think, now in the community. I know Phil Hopkins and Dan Cheverino have done very similar things. And I think it's really important to do this in order to capture the time evolution of these different feedback processes, because the time steps in our simulations are not millions of years, they are even down to hundreds of years. So it may be important to capture this time evolution. So we put this into the adaptive measure refinement code Ramses by Romain Tessier here. One thing I won't have time to talk about in this talk is some efforts we've done in studying cosmic ray feedback, which is a very interesting avenue for driving galactic winds, but maybe in another talk I can mention something more about this. So I just told you that the initial momentum injection rates from these sources are roughly equal. That is a bit of a lie. In reality, you can have different kinds of boosts, right? So for the radiation field, if you're emitting a lot of starlight or UV in a dusty, dense star-forming region, your photons can bounce off dust grains, and therefore you get a momentum boost by some factor that's roughly the infrared optical depth of the star-forming region. A similar sort of thing exists, of course, for supernovae. As you know, the Sedov-Taylor phase of a supernova explosion is very successful, or if it is successful, it will generate a lot of more momentum than the initial blast momentum. So these are sort of calculations or fits to 1D simulations done by, for example, Blondin et al. Or Thornton et al. 98, where if you have a successful Sedov phase, you can get up to 10 or even tenths of the initial blast momentum input. And of course, the success of all these extra momentum generation strongly depends on environment. It may be that we are, not resolving the shocks that dissipate most of the energy in these bubbles. We may actually also have, these shells are being accelerated, and we can have really Taylor instabilities occurring, as been argued by Mark Krumholz and Thompson just recently. So these are issues that we need to consider. In regards to the energy injection and evolution, we should also know that in these kind of cosmological simulations, the thermal feedback is usually inefficient because the gas cooling time is very short in dense gas. And this is something that people have tried to do, workaround tricks for. The most successful ones has usually been sort of type, adiabatic evolution types, the popularized via the blast wave feedback in gasoline by Greg Stinson and collaborators, but I think it was pioneered by Gerritsen in '97 actually. You can also find other ways of making thermal feedback more efficient. You can think about invoking runaway stars, which may be up to 30% of runaway O stars in these sort of massive star clusters, which will lead to more efficient retention of the hot gas energy. Or even just if we enforce large temperature jumps via selective energy deposition, which is done by De La Vecchia and Job Shea, or even have an explicit model for superbubbles, which is what I think Keller and James Wadsley has been working on just recently. What we do here is something a little bit different. So we actually solve for two energy equations. So we have the usual thermal energy equation. We also invoke a second sort of feedback energy equation where we put some little fraction of the thermal energy, which we think should be evolved over some crossing time of the gas sort of resolution elements, let's say 10 megayears. Okay. So this should be sufficient enough to drive this extra momentum that we don't really, that generation which we don't really resolve in these cosmological simulations. So to be, so I think to test what this prescription is doing, I think it's very sane to first look on the smaller scales what's going on. So what I'm going to show you here is a very simple setup. This is sort of a patch of gas at the resolution almost affordable in our cosmological runs. This is sort of 10-ish parsec resolution. And we are just letting it form stars using the same recipes we heard about in the past days. And we're looking at sort of this evolution here in density and temperature. On the right-hand side, I'm showing you different simulation where we have increased complexity. So we have no feedback here. Then we turn on the energy. We have only momentum in one here. And we have this all-in model here in black. Okay. So this is what should happen in a patch of the ISM that we are resolving in our simulations. And the sort of conversion efficiency as a function of time is leveling out at around 8%, which seems reasonable for a GMC of this high mass, like 1 million solar masses. It's not. It's sort of qualitatively in the range of Evans and Murray 2011. We then go to larger scales, and this is now a Milky Way-like galactic disk, and in fact it's the Agora initial conditions, which we're going to talk about more later in the week. So here we can study, what we did here was focus mostly on how star formation proceeds, so how efficiently do we regulate star formation in this disk. And what we were showing here is that when we compare our simulated data here, these squares to the data by Big L or the older one by Kennicut 98, if we don't have any feedback, then we are very sensitive to the input efficiency per freefall time that we assume in the gas. Okay, so we're almost rescaling it by the sort of the ratio between the two. But if we use the feedback I just talked about, then we are basically completely insensitive to the input efficiency. We are regulating this to a level which seems reasonable according to observations. So all this is nice. It's a good sanity check, but it doesn't tell us at all about the baryon cycle, right? So how do we actually work against a cosmic accretion, or how do we regulate the metal content and gas content of these systems? So to do this, we go to cosmological simulations. So these are zooming simulations of a galaxy forming in a 10 to 12 solar mass halo at redshift 0, so like a Milky Way-like galaxy. So we have a forced hydro resolution around 75 parsec in this one. And we account for all the feedback I just mentioned to you before. And we do star formation based on local dust shielding models. So basically an H2 molecular hydrogen formation model suggested by Krumholz, McKee, and Tomlinson in 2009, which has also been calibrated by, on full chemistry networks with, so it compares very well to what, for example, Charlotte Christensen and Nick Nidden have been doing in the sort of full chemistry models. Okay, so now we're getting to some interesting things. So now we can return back to this question: which models of star formation and feedback achieve reasonable characteristics? So before I do this, I want to talk, for 30 seconds about the choice for the conversion efficiency that we're going to use. So I told you just before that we're using a Schmidt-like law for how we convert gas into stars. The star formation timescale here is the freefall timescale over some efficiency of freefall time. And on large sort of KPC scales, star formation is of course very slow. This is known from the Thing survey, by Big L and Leroy. I think had a few pioneering papers on this, showing that the efficiency per freefall time on large scales is more like less than 1% even. So I think it's 0.25% for the Milky Way, probably 0.5% to 1% for in this Things sample. But if you go to individual GMCs, it's much less clear. Okay, so it may depend on environment, and there's some discussion on this in papers by Evans and Murray. What I'm showing you here is a sample of derived efficiencies from the literature, so Evans, Lada, and Murray, and there's a huge spread. Okay, so it can be anywhere from 0.1% to tens of percent. Some of this may, of course, be just evolution of the clouds, but we're taking these at face value just to sort of see, how we are affected by this, or how the galaxies are affected by different choices. So we can investigate somewhere between 1 and 10%, which seems reasonable. What I'm going to show you now is that stellar feedback-driven outflows are necessary to simultaneously predict a slew of observed inferred characteristics, such as the cosmic star formation histories, stellar mass-halo mass relations, the mass-metallicity relation, Kinetic-Schmidt relation, blast rotation curves, etc. But the way in which this is achieved actually matters, and I come back now to the Ouroboros again. So it matters really, like what how we do each step of the star formation and feedback models. Okay, so I'm going to now contrast a few different models. So let's say focus on star formation. I'm gonna show you what's going to happen if we pick a low or high star formation efficiency per freefall time, 1 or 10. And the thing is that a very inefficient star formation mode tends to smear too much of the energy across your disks, which leads to a very low, non-correlated feedback, which doesn't give you winds. So I'm going to show you that a high efficiency can give you much more heating and therefore correlated feedback and galactic winds. Or you can just cheat and keep a low efficiency by hand, which is what observations tell you on large scales, and just dial up your feedback by hand, which is something that has been done previously in the community, and that should give you roughly the same result, but there are some very stark stark contrast between these models, as I will just show you. Okay, so let's have a qualitative view around redshift 3 of these different models. I'm going to show the gas density, gas temperature, and gas metallicity in sort of like a 100 kpc map around the galaxy. So first of all, we have this inefficient star-forming galaxy. So the Schmidt relation efficiency is 1%. We still have all this fancy feedback in, but as you can see here, all of the metals are trapped in the ISM. There are no outflows. The gas is pretty compact. You have the cold streams feeding the galaxy, but you have no outflows. And the hot gas around the galaxy is just, given to you by the shock heating of infalling gas. Okay. If you increase your efficiency of star formation, suddenly you have much more turbulent system. You have huge bipolar outflows. You can see this in the metal maps. And the hot gas extends much further than the virial radius. So you're completely dominated by the feedback in heating the gas in this case. Much more turbulent system, much more outflows. The same thing can also be achieved by going back to this inefficient model and by hand dialing up your feedback strength. Okay? You get roughly the same outflow properties, you get a very turbulent system, and it seems like these two models are degenerate for some reason. And we can continue looking at other things like the star formation histories. So here's the inferred star formation history of a Milky Way-like galaxy, stolen actually from Peter Bruzzi. What happens usually in models with efficient outflows is something like this. You burn a lot of gas at high redshift, you form a very compact system, and you're already sort of you're already getting a galaxy that looks nothing like a galaxy we observe today already at redshift of a few. And if you have an inefficient star-forming galaxy, no outflows, you're not doing much better. You're regulating star formation somewhat, but not efficiently enough. And then these two other models that look roughly the same are both falling on top of this relation. Okay, so the black line is this inefficient star formation model. The red line here, the red dashed line model, is the one with boosted feedback. Okay, so again, they look qualitatively the same, slightly different here, but they're both matching this data. And another way to look at the same data is look at the stellar mass halo mass relation. Again, these two models, they are following the derived relation from Peter's work really well. All the other models that we tried where we have inefficient outflows immediately go to the cosmic baryon fraction, of course. We can look at the mass metallicity relation. So this is quite interesting. So here we are looking at redshift 3 to 4. Here we have data by Maiolino et al. And the Tremonti et al. Data at redshift 0.1 is sitting up here. The models that agree with the star formation histories are sitting roughly on this relation here, while all the inefficient sort of outflow models will immediately, they will sort of evolve, out of this relation and towards the redshift 0 relation very early on. At redshift 2 to 2.5, we see a similar thing. The preferred models are again sort of roughly in this relation here, while the other models are already highly enriched and evolved off the observed relation. So this also tells us that when, without enriched winds, galaxies will rapidly evolve off this relation already at early times. So it's not enough to match only a redshift 0 one. That's pretty easy. You can just, overcool your simulation, and you will pretty rapidly end up at the redshift 0 relation. So it's very important to look at this observable at different epochs. And I think this was also argued in Alison Brooks's work from 2007. Okay, so can we break these degeneracies? So these again are these two models that match all the data, but let's look at just qualitatively at the evolution of the gas density around the last major merger happening close to redshift 1. So here's the last major merger. You see, you actually don't even see the second companion of this galaxy here because it's blown out all of the gas. So after the last major merger, the one where we have, let's say, feedback being regulated by high star formation efficiency, we enter an epoch of disk formation after this point. It's very turbulent, of course, but it settles into a nice, well-defined disk that calms down over the period of 8 gigayears. However, this other model where we just by hand say that feedback should be efficient everywhere, even in regions of low star formation densities, the gas can never settle into a cold disk. It keeps exploding. It's never resting. Okay, so these are very different sort of course galaxy evolutions, and this is one way to break the degeneracy, and we can look into other observables to be a bit more quantitative. So, for example, the Kennecke-Schmidt relation at redshift 2 to 3 is a good one. Here we can see the simulation here as these blue points, and we're comparing now to data by Reinhard Genzel. So the CO data at redshift 1 to 3, or data from Lyman break galaxies or DLAs by Rafelsky and also Wolf and Chen. So in one case, we're following on this relation. Too strong feedback will renormalize your entire relation, so it will be in quite a somewhat of a tension with the observed Kennecke-Schmidt relation. So this is something that can be a useful check. We can look at the mass loadings of the winds. So again, here we have the mass loading will just be the mass flux at some radius divided by the star formation rate of the galaxy. Okay, so per solar mass of star you form, how many solar masses of solar mass of gas do you eject? So this preferred model has a very high mass loading at early times. So this is a function of circular velocity of the main galaxy. Okay, so in the youth of this galaxy, it's a very high mass loading factor of roughly 10, and it decreases towards redshift 1-ish. And actually, I haven't plotted this here, but at redshift 0, it's actually below unity. So there's some fall off with time. These sort of boosted feedback models are always too high. Okay, it's above 10 at all times, which makes the galaxy never rest. You can't form a thin disk without any feedback or weak outflows, you're always below unity, so you don't regulate the baryon fraction. And of course, it's a lot of scatter here. So for fun, I plotted one of these mass loading versus circular velocity that, from where circular velocity scales, the mass loading scales a circular velocity to the power -1, which is to be a momentum-driven wind scenario. As you can see, it can easily just be an energy-driven, which would be -2, because in reality, these factors are very stochastic in nature, and there's a lot of scatter. So that is in sort of stronger contrast with these sort of imposed models of winds from, let's say, Oppenheimer and Dave, and maybe also what is used in these latest ARIPO simulations. So one thing that I find interesting is if you look at the wind velocities as a function of circular velocity, they are, it's a lot of scatter here, but they are roughly the same in all of these simulations actually. So wind velocity seems to just come out roughly the same. And these are, in the same ballpark as the observed ones by Schwartz and Crystal Martin and Rupke in 2005. So far we don't make any strong claims about this, but yeah, wind velocities are in the ballpark of the, sorry.
Yeah. Can I ask just a basic question? When you say you're measuring wind, like specifically where are you doing it, and how do you, like, is it at the material?
No, so here we just, I was just, sorry, it's a little note here. We just average out the 20 kpc of the disk. So it really matters where we measure this, right? And so we haven't made any more, as long as we're doing the same thing for all these galaxies, it's fine. But yeah, to compare to observations then properly, then I would say we need to do some more work, Okay, so a few more slides here. But so we can also look at the galaxy mass, stellar mass relations. So here we have the models I just discussed before, where here we have tons of data from literature that we just put together. You can see the references here. I think the sort of the shaded region here is from Bernardi 2012. And these are the evolutionary tracks of our simulations. So the line here is showing this regulated model where we are matching the data at all stellar masses, while in the boosted feedback one we get a sort of more of a stellar halo-like object where we are overestimating the galaxy size. And without any feedback, we are in the overcooling regime, so we are clearly not matching this data at all. And just morphologically, of course, as I said before, one is a dusty mess or ball of gas, and this scenario here is a fairly nice spiral galaxy with a distinct, sort of relatively distinct thin disk. Okay? And this is, again, the same initial condition, the same feedback, or the same star formation, the same feedback with slight changes to these parameters. Finally, we can look at the thin and thick disk, derivative 0. This is something that's in preparation now. So this is the rotation curve of this final disk that we have. And here we can actually start looking at different components of the disk, I think for one of the first times. So we can look at young stars in the galaxy, so 0 to 4 gigayears old, and have another component which is the old stars, let's say 4 to 13 gigayears. This is a bit arbitrary for now. And I'm plotting in these sort of the V over sigma as a function of radius in the disk, and comparing this to Bovie et al. for at the solar radius. And we're seeing some sort of thick-thin disk dichotomy, which previously hasn't really been possible, I would say, because feedback or strong feedback seem to destroy all the signs of a thin disk. And I think we are here getting a little bit closer to getting so several components or some sort of thin-thick disk dichotomy. So finally, I just want to mention that what's actually going on when we're playing with these efficiencies is that we are making actual claims about how correlated not only feedback is, but how correlated star formation is. So we should be able to make claims about the mass function of young star clusters, for example. So what I'm plotting you here is for these different models, low and high efficiency of star formation, and I'm comparing sort of the mass function of young star clusters, which means sort of star particles in this case. It's a function of cluster mass here. And this is sort of and I'm comparing this to some data from Larsen et al. For cluster-rich spirals. And this sort of tiny, fairly tiny difference in mass function is what gives rise to these different galaxy evolutions. So if once you capture some of these more massive star clusters, that's when you sort of punch hole in your disk and you more efficiently drive outflows, while in the other one, you are not energetic enough locally to do this. And you can be a bit more quantitative about this and look at the mass flux from these different disks. So the mass flux coming out of the disk, this is at the same star formation rate, okay? The mass loading or the mass flux is much higher in this case than this case, just because the most massive star clusters seem to do a lot of work on getting the gas out. And of course, to actually be quantitative about this, ultimately we have to understand what sets the efficiency of star formation on small scales. We have no idea, or we can't model it on these scales, so we probably need to connect this to more detailed models of star formation in supersonic turbulence, for example, which of course is a whole new field, but I think it will be a good effort to try to make that connection in the future. Okay, so I think I've run out of time, so I'm just going to put up my conclusions here and end there.
So we have about 4 minutes for questions.
Just a quick clarification. You were showing the mass size plot to put it up back again. You were matching the high, on that side, but I got the impression you were doing that with pure disk galaxy or something like that when you show the picture, and that would be the trend where we see the spheroids. Maybe I misunderstood.
So you're referring to this plot here, or?
And the picture that you showed the galaxy corresponds.
Yeah.
Yeah. So those galaxies that we see in the universe are not this nice, this bulgeless, this that you're showing there.
I mean, so this.
You're making those sizes with this kind of.
I mean, so here, some of the data points here are just blue galaxies, local blue galaxies. Some of these are from, again, the things galaxies, for example, and some will be just in the local universe, and right. So, and this will be more of an maybe SB galaxy. So.
Actually, this has moved from a budget, so maybe the question is, do you reobtain the right distribution of some of that sequence?
Sorry. Okay. Yeah. So we have only like a few of these simulations. So I think we really need to go get more statistics, do more simulations. For now, we only have a few, and that's a problem for the whole community. These are very expensive runs.
But
So.
then what you get out of a few is this kind of galaxy. I gather that there is a sort of issue. This galaxy should not be this bulgeless or almost bulgeless masses inside.
So I'm not sure I understand the points.
Don't get a bulge.
Yeah, I mean, it has a bulge. I mean, it's. No, but I mean, if you do a decomposition of the surface brightness, then it will be sort of bulge to total ratio could be 15% to 20%. So yeah, we've done this. Yeah.
This is good. This does happen in the real universe, and most hydrocids overproduce bulges, so it's actually kind of nice to underproduce it.
Yeah, I mean it's. It's not.
But if we make them attend to the 11 and the field galaxy to get there is this, then I think we are working.
So at the stellar mass that this is at, so 6 times 10 to 11, then half of the galaxies are early types, right? And pure disk will be a very small fraction. And so this is not a pure disk galaxy for sure. So again, it's an SBC maybe galaxy. So
we have time for one more question. Edmund, do you want to come up? Sure.
You mentioned the equation, the equation that stores the energy from feedback.
Mm-hmm.
On 10 million years. Have you, because 10 million years is a lot of time feedback. Have you tried different steps?
Yeah, between 1 and 10 mega years. So this is sort of the roughly the crossing time of the coal ISM, or maybe several crossing times of a GMC. So and if you go down to 1 mega year, you change the final stellar masses probably by 50% or something like this. So this matters, right? So how this is set. It's not like a regulating parameter, and this is that's still a caveat. So.
Great. Thank you.
So radiation momentum injection as well. So the volumetric luminosity of starlight over the speed of light. So all of these, the momentum injection rates from all of these different mechanisms are roughly the same, and this is probably why we should consider all of them in our simulations, or try to understand anyway if any of these are more important than the other ones. So this is what we have done. So this is here's a matrix of the terms that we have in our feedback recipe. So the energy injection is coming from supernovae and the stellar winds. Momentum is coming from supernovae, stellar winds, and the radiation. And we have mass loss and metal enrichment from various sources. Okay. So, and these are all again calibrated on stellar evolution codes like Starburst 99. And this is something that's been more popularized, I think, in entities. But in reality, of course, everything is connected, as you're probably well aware of. So star formation will generate a certain properties of feedback, and feedback will generate in turn outflows and turbulence in the interstellar medium and in the intergalactic medium, which in turn influences star formation and so on. And the big question is for modelers is, so which models of star formation and feedback achieve reasonable galactic characteristics, and are galaxy formation models degenerate? And if so, how can we break those degeneracies? Do we need just more data, or what can we do? So I'm just going to start from the feedback scale, and this, what I'm showing you here is the luminosity output from a single stellar population taken from Starburst 99. And so it's the luminosity is a function of time, and I'm plotting you here the bolometric luminosity of the starlight, the wind power or the wind mechanical luminosity, so of the stellar winds from young massive stars, and the mechanical luminosity from supernovae. Okay? As you can see, supernovae explode only after roughly 4 megayears after the birth of a single stellar population, and before this time, stellar winds and the radiation field from the young stars have already preconditioned the star-forming regions. And what's interesting from this plot is that the momentum injection rate from supernovae and winds have roughly the same magnitude, the L mechanical over the typical velocity, a few thousand kilometers per second for these processes. And that happens to be roughly equal to the So I'm going to talk about a few numerical experiments that I've been working on the interplay between star formation and stellar feedback in galaxy formation simulations. And this is work I've done together with Andrei Kravtsov and Nick Lydon at the University of Chicago, and also Sam Leitner. So I don't think we have to reintroduce the issues that exist in galaxy formation theory, but so I'm just going to jump straight into how I view the sort of star formation feedback cycle. So this is an Ouroboros, so the serpent eating its own tail. And the problems that we usually have is that we are thinking about star formation and feedback as separate now in the community. I know Phil Hopkins and Dan Cheverino have done very similar things. And I think it's really important to do this in order to capture the time evolution of these different feedback processes, because the time steps in our simulations are not millions of years, they are even down to hundreds of years. So it may be important to capture this time evolution. So we put this into the adaptive measure refinement code Ramses by Romain Tessier here. One thing I won't have time to talk about in this talk is some efforts we've done in studying cosmic ray feedback, which is a very interesting avenue for driving galactic winds, but maybe in another talk I can mention something more about this. So I just told you that the initial momentum injection rates from these sources are roughly equal. That is a bit of a lie. In reality, you can have different kinds of boosts.